Let's see. This is a shout out to Ashley. We're missing Ashley today. We're missing Mallory. We hope you guys are doing well. And we hope to see you back soon. So the domain is simply the inputs. And what you want to think of when you think of the inputs is all of the available numbers that exist on the x-axis that you could plug into the function. Okay? What are all those available numbers that you can use? The range is the outputs. And we still think of a number line. We just think of a vertical number line. What are the available values that get produced? Okay. So we have two objectives today. Number one, we want to be able to look at a function or a relation and be able to determine the domain and range by looking at it graphically. We would also like to be able to look at an equation and determine the domain. The first is going to be easy. The second one's going to be challenging. Right now, take your time to draw these 6 relations onto your paper, because I didn't get them in for copying. Sorry. I'm a bad teacher. And I'm proud of it. Okay, here we go. So when I determine the domain, what I like to do is I like to take a vertical line and drag it across the graph. Okay? So for example, right now I'm sitting at a position of -6 on the x-axis, right? Does the graph have an output anywhere for an x value of -6? No. Does it have an output anywhere at -7? How about at -5? No, there's no graph here. However, if I move over to -3, does the graph have an output at -3? What is the output of the graph at -3? What's the height of the function at that spot? 5. Yeah. You plug in -3, you get 5. In fact, you can see that you start picking up values right after -4. The open circle means that you don't have a value at -4, but rather directly after -4. So therefore, the domain of this function begins with -4 to -1 bracket. And then there's no values that produce an output between -1 and 1. But once we get to 1, we pick it back up and we go on over to 4. Everybody okay with that? We're doing that? Now I'm going to do the range. And for the range, I like to drag a horizontal line. Oh, you're going to do that. Okay. There. Oh. Don't let go. You might lose it. Whoa. Okay. All right. All right. Is there any output down here? Here? Here. How about here? What's that output? Anything after that? How about here? So I just got 2 and 5. Not everything between 2 and 5, but just 2 and just 5. How do we show just 2 and just 5? Roster. Does that make sense now? So if you saw 2, 5 bracket, that means every number that exists between 2 and 5. This means only the numbers 2 and 5, like you would list a roster on a volleyball team. Okay, look at the next one. Start dragging lines. Is it going to cross over here? It is. It's got an arrow on it. It's going forever down and over this way. Cross here, here, here. So from -infinity all the way to 1. We are looking at the x values, -infinity to 1. Range. Stupid line. Let's make a new one. There we go. Okay, is it going to cross down here eventually? Yep. How about here? 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 So from negative infinity to 4. Good. It's going to cross over here? 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 How about the horizontal line? Stop doing it. It's going to cross down here? 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 Crosses everywhere, right? We got negative infinity to infinity and negative infinity to infinity. I wasn't having these problems last hour. I don't know what's going on. All right, are we going to have domain values here? No. How about here? 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 So between, yeah, -5, -1. Range? Negative infinity to infinity. You try the last two on your own. Did you go from -7? I should have had an arrow on here. Sorry about that. No, so the idea is that for this domain, is the graph going to cross this line at some point? Yep, it's going to produce, if you plug in -7, it's going to have an output, so on and so forth, all the way across. So anyway, take 7 minutes, work on this, then we move to the next piece, okay? You want to check answers are posted? 7 minutes, go. Okay, here we go. So we flip it over, and now things change a little bit, okay? And the investigation becomes, if you just look at a function rule, can you determine by looking at the function rule what the domain is? Forget about the range for a second, but can you determine the domain? So we just had you look at situations where you had a graph, and what I'm asking you right now is, of all the numbers from negative infinity to positive infinity on the number line, what numbers can you plug into x squared and what numbers can't you plug into x squared? What do you think? Hearing some good thoughts. All of a sudden our brain goes to mush, right? This is simply the question. If you plug a number in, do you get a number back out? So let's just try some. Like 0. 0 squared? 0. Could you plot that point? Yep, so that means that 0's in your domain. 5. 5 squared. Could you plot 525? So 5's in your domain. Let's try a negative number. -10. -10 squared. 100. Could you plot -10, 100? So -10 is in your domain. Can you think of any number on the number line that you wouldn't be able to plug in and come up with a result for? No. All real numbers. Now here's the thing. You actually know what x squared looks like, don't you? It's a parabola. If we would have just drawn the graph, you would have said negative infinity, positive infinity, right? See how they match together? The more you're able to think about table values, a function rule, and a graph, the better off you're going to be in math. Okay? A lot of times people say, do we have to graph it? I graphed everything. It didn't matter whether the direction set or not. I always wanted to know what the graph looked like. That was helpful to me. Now, here's the tough thing. You don't know what that graph looks like yet. I'm going to put it up here right now. Okay? It's a crazy graph. I'm going to teach you how to graph these as quickly as I graphed it right now in a few days. You're going to learn how to do that. because you're super smart. That's what you are. That's what it looks like. Now, this is different because it's a fraction, right? So what values, think of the same thing. I've got a number line. Are there any numbers you could not plug into there? Why 3? That creates a 0 in the denominator. Look at the graph. What value is not part of the domain? 3. That's where there's no graph. Okay. These dashed lines are called horizontal and vertical asymptotes. They're not actually part of the graph. They just help you draw it. But this graph does not have a defined value at 3. So therefore, the domain goes from negative infinity to 3, union with 3 to positive infinity. How about square root functions? Think of the number line. Are there numbers that you could not plug into that square root function up there? If I plug in negative 3 plus 4 is 1, and the square root of 1 is 1. So negative 3 works. Negative 5 plus 4 is negative 1, square root of negative 1. Imaginary world, right? So there's definitely, can somebody think of another value other than negative 5? Negative 6, negative 7, negative 8, so on and so forth, right? In fact, if you looked at the graph, you would be determined to understand that it would be from negative 4 to infinity that we had domain values. And as you said, anything to the left of negative 4 does not work. So it raises a question for us about what are the types of functions that have restrictions and which ones don't have restrictions. And although this is not a complete overview, it's a pretty good overview. If you have a polynomial, like say y equals x cubed minus 2x squared, you're totally good to go. There are no domain restrictions there. All real numbers, no problems. Suppose you got y is equal to x to the 5th divided by 6, and you're like, uh-oh, I've got a fraction. Doesn't matter because that fraction doesn't have a variable in the denominator. This is just like 1/6 times x to the 5th. If you've got a polynomial, you are good to go. There are no polynomials that have restrictions. You see a polynomial, all real numbers, right away. But suppose you got a rational expression. Well, we saw that that causes issues. Suppose 1 over x plus 5. What can x not be in that scenario? Negative 5. Suppose you have y is equal to 2 over x squared minus 1. What could x not be in that scenario? Plus or minus 1. Suppose you had y was equal to 1 over x squared plus 4x. Well, now there's two values that it can't be. You factor out the x, and you would end up with 0 and negative 4, right? So those all have restrictions that you have to eliminate. You're like, well, which ones wouldn't have issues? Well, here's one. You're going to have to think about this for a while. Six over x squared plus 1. There's no problems with that. None at all. Why? Very good, Dane. Dane is an excellent mathematician. Did you watch the video ahead of time? Okay, x squared plus 1. Dane understands if you square something, it's going to be positive or 0. But then when you add 1 to it, it's for sure going to be positive, correct? There's no way you could produce 0 in the denominator. I want to make this clear again. We talk about graphing things. You guys told me that this would fail at what two values? What two? Plus or minus 1, right? And if you were to graph this, it would be a parabola that would be shifted down 1 unit. Well, sure enough, it has 2 spots where it's equal to 0. Think about the graph of x squared plus 1. It's shifted up 1 unit. Does that ever cross the x-axis? No, it's never equal to 0. That's what it means to cross the x-axis. So you can see it has no issues. Here's another one. Y is equal to 5 over x to the 4th minus x squared. Whoop, not minus x squared, plus x squared plus 2. If I didn't put the plus 2 on there, then I would have had 0 would have been a value that wouldn't have worked. But in this situation, x to the fourth plus x squared plus 2, that's definitely always going to be positive, okay? Radicals with restrictions. How about this? Y is equal to the square root of x. Y is equal to the square root of x. Can't take the square root of what? Negatives. In fact, you could have y is equal to the square root of 3 minus 2x. That causes a problem as well. Here's another one that causes problems we haven't talked about. Y is equal to the fourth root of x. You can't take the fourth root of negative numbers either. But here's one that you are okay with working with. Y is equal to the cubed root of x. Now, you try to get smart. You're like, well, Mr. Gantz, if you plug a negative in there, like -1, then that doesn't work. Well, what is the cubed root of -1? -1. Because -1 times -1 is 1, times -1 is -1. So you can see that there are no issues there. In fact, if you have the fifth root of x, you're not going to have any problems there either. Odd roots don't discriminate. Sometimes even roots don't discriminate either. And here's one last example. The square root of x squared plus 1. Why am I okay to take a square root and have no restrictions in that situation? Because x squared plus 1 will always be positive. See that? See why this is a little bit trickier than simply looking at the graphs? You have to think about what's happening. So let's give it a shot. Flip it over. You tell me what the problem is. What's the issue? Or is it just all real numbers? Can't take the square root of negatives. So therefore, I have to make it positive. X plus 2 must be greater than or equal to 0. I set up the inequality because I can't take the square root of a negative. So I make it so that it's not negative. Subtract the 2, x greater than or equal to -2. So that means -2 to infinity. X squared plus 3. It's just a polynomial. What's the domain of a polynomial? -infinity to infinity. All real numbers. Uh-oh, for number 12, I have a rational function. I can't divide by what would produce 0? So I got -infinity to 4. Union with 4 to infinity. '12, I got a cube root. Is there any problem with cube roots? Nope. For 13, I've got a rational function. Can you take, or we can't divide by what? So I factor out the x, and I get x times x minus 5. What would produce 0 in the denominator? 0 and 5. So therefore, I go -infinity to 0, union with 0 to 5, union with 5 to infinity. For number 14, I have a fourth root. Do fourth roots have issues? Big issues. Yeah, we got to make sure it's positive. So we say that 7 minus x must be greater than or equal to 0. Subtract the 7, -x greater than or equal to -7. Divide by -1, x less than or equal to 7. So -infinity to 7. You know what the most common answer for number 15 is on the test? Is that accurate? X can't be 5? Am I allowed to plug in 5? But I get 0. It's okay to get 0, right? Like 5 minus 5 is 0. Can you plot that point, 5, 0? Yeah. But if you had this, 1 over 5 minus x, is it okay to get 0 in the denominator? No, because if you plug in 5, what's the output? The output is undefined. You can't plot that point. But here you would plot 5, 0. You can plot that point. So this is just a polynomial. So what's the domain? All real numbers. Sweet. Love all real numbers. 16, is it a problem to divide by 5? Nope, all real numbers. Uh-oh, 17, I've got a rational expression. So I can't divide by 0. Is x squared plus 1 ever 0? Oh, so all real numbers. Oh boy, now Mr. Gens gets difficult. Are square roots a problem? Big problem. 3 plus 2x minus x squared must be greater than or equal to 0. Fortunately, my college algebra teacher yesterday told me that if I'm solving a non-linear inequality, I have to set up a graph. So I'm going to multiply through by -1 to get positive x squared minus 2x minus 3, and that would be less than or equal to 0. Does that factor? X minus 3, x plus 1. So I look at the graph, it goes through positive 3, and it goes through -1. Is this a parabola that goes up or down? Is it a positive x squared or a negative x squared? So therefore it goes up. Okay, parabola goes up. Am I wondering where it's above the x-axis or below the x-axis? Below. It's below the x-axis between -1 and 3. So that's the domain. Now you're like, ooh, that one could be tricky on the test. I'd say all these are fair game on the test. You want to make sure you get this. Your worksheet's going very similar to this, okay? You want to know. This is your last topic that you need to know for the final exam. We'll be practicing it the rest of the week. F of x equals square root of x squared plus 2. Uh-oh, can't take the square root of? Negative. So x squared plus 2 must be greater or equal to 0. Oh, my teacher told me that if you want to solve a quadratic inequality, you need to make a graph. Does it factor? Nope. Do you know what the graph looks like? Yeah. Shifted up 2 units. Are we wondering where it's above the x-axis or below the x-axis? Above. Is it ever below? No, it's always above. So what's your domain? All real numbers. Uh-oh, we got another radical. I got a square root. Got to make sure that it's greater than or equal to 0. My teacher told me if you get a quadratic inequality, make a graph. Does it factor? No? Do we know what the graph looks like? Yeah, it's shifted down 3 units. And it goes down because it's a negative x squared. So, am I wondering where it's above or below? Is it ever above? It's called the empty set. There's no domain. None. In fact, if you were to plug this into your calculator and graph it, nothing would come up. Just be a blank screen. There's no available numbers plug in there. None. You guys are doing well. Last 2. You guys lead me now. You tell me something important about the last one, or 21. Okay, x can't be 3. I like that. So you looked at the denominator. Tell me something else. X must be greater than or equal to -2. Right? If you look at the top, I mean, if I set up x plus 2 is greater than or equal to 0, I would get x is greater than or equal to -2. So I've got these two things happening, right? Those things are actually in conflict with each other, aren't they? I mean, if you graph -2, x is greater than or equal to -2, does it cross over 3? So we got to eliminate 3 from that solution set. So we go -2 to 3, parenthesis, union, parenthesis, 3 to infinity. That's tricky. How about the last one? Tell me something intelligent about the last one. Good. So the top, so Asher sets it up, x plus 4 has to be greater than or equal to 0. So x is greater than or equal to -4. What about the bottom? You say it's fine because why? It's a cubed root. But the problem is the cubed root sits in the denominator. It's fine except for one value. I can't come up with what in the denominator? What would produce 0 in the denominator? 2. So x still can't be 2. I mean, your first inclination is, hey, it's all right. It's a cube root. But if it's in the denominator, we still got to avoid where it gets to be 0. So are these two things in conflict with each other? You better believe they are. You plot -4 greater or equal to 0. Do you cross over 2? You sure do. You got to eliminate 2. So -4 to 2, union with 2 to infinity. Man, you guys are smart. Just think if you weren't. These would be impossible. Ashley, if you're watching the video and you come back and say, you know what, nothing. Sorry. You waited this long. Should we give her a prize? What do you think? A high five. There you go. If you say that Dane rocks, then I will give you a high five. There you go. All right. Later.